Right, this is going to be me going through the 2025 Unit 4 Applied Maths. I'm going to do the stats and the mechanics. Okay, so question 1 in section A, the stats section, and again, just to remind you, we need to be showing all of our methods, okay, don't skip any steps, because you want to be able to get all the marks, even if you get the answer wrong. We need to be able to see what mathematical method you use so that we can award marks. Okay, so any calculation you do on your calculator, I'd encourage you to write down on here. Okay, kicking off question 1, part A. Continuous random variable is uniformly distributed, so that's the first thing that pops into my head, uniformly distributed. We know that the mean is 7.5 and then the variance is 3, and we don't know either of the endpoints of the distribution, so this feels to me like a simultaneous equations question. So let's have a look. We've got x, let's use the right pen, bad start. X is uniformly distributed C D. We know that the mean of x, which remember is d minus c over 2, the middle, the mean value, is 7.5. So I can say that d minus c is 15. And then there's my first equation. Variance of x, which remember is d minus c squared over 12, and that's equal to 3. So d minus c all squared equals 36. It was a very bad start to the first question because I got the mean value bit wrong. It's d plus c and c plus d in those two equations. And so then I can say in this one, d minus c, well, I'm going to square root both sides, is plus minus 6. But because we know d is bigger than c, we know that d minus c is positive. So we get d minus c is positive 6. So I have d plus c is 15, d minus c is 6. So I'm going to call that equation number 2. I'm going to add them both. So I get 2 d's are equal to 21. D is equal to 10.5. And then that means that C is 15. Take away 10.5, which is 4.5. And there's my answers. Okay, moving on. Okay, so we've got Selena doing some multiple choice questions, multiple choice tests with lots of questions. And we've got up here in the first section, we've got that she is very confident on 0.2 as a proportion, 0.2 of the questions, and if she's very confident, then she gets them right 0.9 of the time. Okay, she says she is confident with 50% of the questions, and if she's confident, she gets them right 70% of the time. And then finally, she says she's not confident with 30% of questions, and she only gets a quarter of those questions correct. So part 1, calculate the probability she'll get the answer correct. So let's call that the probability of C. I should probably define C as the event that she gets a question correct, but I'm not going to. And then she can be very confident and get it correct. She can be confident and get it correct, or she can be not confident and get it correct. And I'm going to type that into my calculator and add them all together, 0.605. Okay, so there's just over, or nearly a 61% chance that she gets the randomly chosen question correct, sorry. Dotty 2, given that she got it correct, calculate the probability she was not confident. So we want the probability that she's not confident given that she got it correct. So that is then going to be the probability of her not being confident and getting it correct over the probability of her getting it correct. Okay, so the probability of her not being confident and getting it correct is 0.3 times 0.25, and then the probability she gets it correct is 0.605. And again, I type that into my calculator and I get 0.1240. Okay, and there's my answers for the first two parts, so nice 5 marks there. Moving on. Okay, looking at this question, slightly different setup. She's got a different set of questions now. She knows the answer, so the probability she knows an answer to the question is P, and she gets that right 100% of the time, which means the probability that she does not know the answer to the question is going to be 1 minus P. And in that situation, she will then choose one of the 4 answers at random. So if she doesn't know the answer, she's got a 1 in 4 chance of getting it correctly because she'll just be guessing. Okay, so if we look then at dot E1, calculate the smallest value of P that will give a probability of at least 70%. So we're going to have some inequalities in here, so let's have a look. Let's go again, probability correct. Well, if she knows the answer to the question, that happens a proportion of P of the time. Remember, P is going to be between 0 and 1 here, and we're going to multiply that by 1. I know we don't need to do that, but for completeness' sake, I will do it. Then this is the proportion of the time that she does not know the answer. And then if she doesn't know the answer, remember she guesses and picks one of the 4 available options at random. Okay, so when I multiply that out, I'm going to get a quarter. And then I've got 1 whole P, take away a quarter of P, so plus 3P over 4. And what I want is that quantity, that probability, will be at least 0.7. Okay, so let's turn it all into decimals. Therefore, 0.75p plus 0.25 is greater than 0.7. So 0.75p is greater than 0.45. P is greater than 45 over 75, which is 0.6, I think. Took my calculator on, 45 divided by 75 here. So P is greater than 0.6. Therefore, min value is P is equal to 0.6. So what we've just figured out there is, if on this test there's a 60% chance that she knows the right answer, then that means when we randomly choose a question, there's a 70% or at least a 70% chance that she will get it right. Okay, at least 8 out of the 10 questions must be answered correctly to pass the test, assuming that she answers the question correctly is 0.7, calculate the probability that she'll pass the test. Now, this feels like a binomial, okay, because what we're being told is we're being told the probability of success, we're being told how many trials are conducted, and we're being told what the number of successes we need is. So if we say let x be equal to the number of correct answers, okay, then we can say that x is binomially distributed n p, okay, and we want to find the probability that x is greater than or equal to 8. We need her to get 8 or more answers correct. Okay, now I know this is on a unit 4 paper, so you're expecting continuous distributions, but they can put discrete distributions on here as well. So that is 1 minus the probability of her getting 7 or fewer answers correct. Now I'm going to type the second bit into my calculator. So just a reminder, we're going to go into distributions, we're going to go into binomial CD. We've got x is 7, n is 10, the probability of success is 0.7. So I get 1 minus 0.6172 and some other stuff, which means the answer, the answer that I'm going to get at the end is 1 minus that. So 0. And remember, we're going to write our answers to 4DP3828. And there we go. Lovely. Moving on. Okay, what have we got going on here? So we've got a city councillor looking at the relationship between numbers of delivery drivers and number of bus drivers. Okay, so there's some words at the start of the question that I don't want us to miss. She's investigating the decline in the number of bus drivers. And then during this time, she finds that delivery companies, so the delivery people, are actively recruiting, which means they're trying to get more drivers. Okay, and so that to me is suggesting that there's going to be some kind of negative correlation between these two things. Explain why a one-tailed test could be appropriate. There we go. It's exactly what I just said, because the counsellor is looking at the link between the decrease of the number of bus drivers with the increase in the number of delivery drivers. The counsellor is looking at the link. I apologise for my handwriting. At the link between the decline of bus drivers and the increase of delivery drivers. She's not interested in something like, well, does the number of bus drivers change as the number of delivery drivers changes? No, she's specifically concerned with the bus drivers declining as the delivery drivers increase. Okay, and if you can read that explanation, well done you. Carry out a one-tailed significance test at the 5% significance level. Right, so what we want to do first is we want to have a look at how many points there are, because that's going to be useful to us when we find the critical value. So we've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so n equals 8. Fine. So if we're doing a hypothesis test, then we want to write down our hypotheses first of all. So H0, remember, is we always say that there is no correlation, and in this case we are testing for negative correlation. Okay, the test statistic that's given to us is, where is it in the question, minus 0.8206. Okay, that's this value here. Okay, then when we go to our table, we're going to look for n equals 8, one-tailed test, 5% significance level, and we'll see that the critical value is, I'm going to put plus minus because it's the size of it we really care about, 0.6215. Okay, then we're going to draw our little diagram. Hopefully yours is better than mine. That's better. So here is our critical value. Okay, anything more extreme than that, and we would say that we've got sufficient evidence to reject H0. Okay, so that's 0.6215. The test statistic, well, we're going to take the positive version of it, so I'm going to ignore that negative. You could draw it going out to the other side here and look at all the negatives if you want. I just don't like doing it that way. This is where our test statistic is. 0.8206. Now that is more extreme than the critical value, so I'm going to say that since test statistic is greater than the critical value, there is sufficient to reject H0. And then always remember this last bit, you must write that in the context of the question. Okay, so that means we have evidence to suggest that there is a negative correlation, and that's really important, we have to say that word, negative correlation between the number of bus drivers and delivery drivers. Okay, moving on. Okay, part C.E1. Why might she conclude that there's a causal link between them? Yeah, I think my answer here would be, if you're thinking about a council or a city or a village or a town or something like that, you've got a finite number of people who are going to be doing that kind of job, because some people won't be able to do it. Yeah, so that would mean that there's a pool of a certain number of people who can do that job, and if some of them are going to be delivery drivers, that means they're potentially leaving their jobs as bus drivers. Okay. The reason why they might go from delivery driving to bus driving would be, I don't know, the delivery driving would be a more attractive job for them. There might be perks to that there aren't for bus driving. They may get more money. They may have to work fewer hours. Anything like that. So my answer would be because there is a limited pool. Oh, can't spell limited. Limited pool of drivers, and conditions working for the delivery company might be better than those for the bus company, and the delivery driver job may be, I'll just say, more attractive than the bus driver job. Like I said before, they may work fewer hours, they may get more pay, there may be perks to the delivery driver job, and so people are potentially going to move from there to the from the bus driver job to the delivery driver job. Okay, what can the City Councillor conclude about recruitment of bus drivers by delivery companies over time? Well, if you think about it, that graph that we had before, we looked, that was just for 8 different cities at a particular moment in time. That may have been taken like in September of a particular year, so she can't actually say anything. Nothing, as she has no data over time. She just has that one snapshot in time. So yeah, she can't make any predictions or anything like that. Okay, moving on. Okay, what have we got here? Oh, a little bit of normal distribution. So X equals the mass of, what are we talking about? Mass of a pack, yeah. And I can say therefore X is normally just distributed with mean and variance. Okay, so I want the probability that x is less than or equal to, it doesn't matter, remember, because we've got continuous variable here. Mass is a continuous variable. So to figure this one out, we're going to go into distributions, we're going to go into normal CD. Our lower bound is going to be a very big negative number, so I use -1 times 10 to the 99. The upper bound is going to be 28. Sigma is 0.3, and then mu is 28.3, and you press equals, and you get the answer of, for dp, remember, 1587. Okay, and that's all there is to it. Packs that have a mass of more than that are classed as heavy. He buys a heavy pack. Calculate the probability this pack has more mass than 29.1. Yeah, so this is actually conditional probability again, isn't it? So we want the probability that x is greater than or equal to 29.1, given that x is greater than 28.8. So we want the probability of both of those things happening. But if it's greater than 29.1, well, it automatically is more than 28.8. So this is just going to be the probability of x being greater than 29.1 over the probability of the pack being heavy, which is the probability of it being more than 28.8. And we can work both of those quantities out. I'm already in normal CD. The only thing I'm going to change is now my lower. I'm going to work out the numerator first. My lower is 29.1. My upper is 1 times 10 to the 99, some massive, massive number. I've already got my sigma and my mu in there. And so I then get an answer of 0.00383 and a bit of change. And then over, and all I now have to change is the lower to 28.8, and that gives me 0.0477, blah, 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 blah. And when I divide the top by the bottom, I get 0.0801. Okay, so if he buys a pack that is categorized as heavy, there is just about an 8% chance, just over 8% chance that he gets a pack of cards more than 29.1 grams. Okay, moving on. Okay, part C.E1. So we've got a histogram there for a bunch of packs of cards. Select 10 packs at random. So that's immediately making me think of X bar. What feature of the histogram supports conducting a significance test on the sample mean? Okay, well, if we have a look at that histogram, it looks like it could be approximated by a normal curve, doesn't it? It looks nice and bell-shaped. Looks bell-shaped, i.e. could be approximated by a normal curve. Okay, because remember that's what we, when we do our hypothesis test or our significance tests, we do them based on normal distributions. And then dotty 2, looking at the number of marks, 7 of them, we're going to be going into a hypothesis test here. So yeah, let x bar be equal to the mean of the sample, mean mass of packs. Okay, and what we're testing to see is whether the mean is 28.3, or whether they are heavier. Okay, so our H naught is that mu is equal to 28.3, and our alternative hypothesis is that mu is greater than 28.3. Okay, if H naught is true, so under H naught, we can say that X is normal, and we're saying that the mean is 28.3. The standard deviation is 0.3, where is it? Oops. What was that? 0.32, so I'm going to square that, and I've got to remember to divide by how many packs are in our sample, and so that's where I get my 10 there. Okay, now it's up to you how you do this. You could look at critical values, you could look at p-values, you could standardize or turn everything into the Z world. Personally, I am a p-value kind of person given the choice, so I want to know what is the probability that X bar is greater than or equal to 285. That was something I forgot to highlight earlier. Our test statistic is that 285 up there. And so again, I'm going to do the magic on my calculator. My lower is now going to be 200. Oh, no, it's 28.5, isn't it? I forgot we've got a sample of 10. So my lower now is going to be 28.5. My upper is 1 times 10 to the 99. My sigma is going to be 0.32 divided by root 10. And my mean is 28.3. And so I've got a p-value of 0.2405. So that's what, 2.4% for reference. And I'm going to compare that with the critical value, not the critical value, sorry, the significance level they've given me in the question. And remember the mantra, if P is low, H naught has got to go. Okay, there is a 2 and a bit % chance that my mean mass of cards in this sample would be more than or equal to 28.5. That is a very rare thing to happen, so we're going to conclude that hasn't happened by chance, that actually the mean mass of the packs is more than that 28.3. So I'm going to write my conclusion now on this next page. So I'm going to say that since that 0.02405 is less than 0.03, there is evidence, there is sufficient evidence to reject H naught. And remember, always finish it off in context. So we've currently got 6 of the 7 marks. We've got to finish it off in context. So sufficient evidence to suggest that the packs are on average heavier than 28.3. Sufficient evidence to suggest grams packs are heavier than 28.3 grams on average. Okay, and you've remember with hypothesis testing, you've got to do your political language. You've got to avoid making definitive or absolute statements. So all we are doing here is we're looking at the data and we are suggesting to Graham whether or not the data supports his hypothesis that his packs of cards are greater, or whether his packs of cards are still the same at 28.3 grams. Okay. moving on. And we're going to go on to the mechanics section next, because that's the end of the stats. Here we are. Right, start in section B now. So this is differential equations and mechanics. So unlike in year 12, in unit 2, where it was 40 marks of stats and then only 35 marks on mechanics, well, now it's 40-40, and they've accomplished that by adding in some differential equations as well. Okay, so question 5, we've got a traffic light hung by some strings. Now in a question like this, I would always avoid the assumption that the tension in the strings are the same, so I always go ahead and start labeling them up straight away. I'm going to call this one tension in B, and I'm going to call this one tension in A. Then I am going to get my different coloured pens, and I'm going to look at the horizontal components of these tensions and also the vertical components of these tensions. Now, I would recommend you do the same thing as I've done here. You get 2 different coloured pens. I always choose red and blue. I try to stay consistent and always do blue as horizontal, but I'm sure somebody will tell me I've used red as horizontal. But develop yourself a system. Pick 2 colours, your favourite 2 colours. One is vertical, one is horizontal every single time, so that your muscle memory is just you draw on these right angle triangles, and you always know that when you do it Newton's second law vertically, you're looking at the red ones, or Newton's second law horizontally, you're looking at the blue ones. Okay, and the last thing I'm going to do to edit my diagram is I'm going to add on the weight of the traffic light. Okay, so those 3 forces in black, by the way, are all measured in newtons. I just leave them off my diagram. And then it's up to you which direction you do first. Personally, I try and choose the easy one first, and to me in this one, that is horizontally, so I'm going to apply Newton's second law horizontally. Because this thing is hanging in equilibrium, that means I can say that left forces take away right forces are equal to 0. Okay, so the blue component of TA minus the blue component of TB must be equal to 0, which is exactly the same as saying the blue component of TA is equal to the blue component of TB. Okay, now in both of these triangles you can see that the blue side is opposite the given angle, which means we're going to use the sine component. So I can say that, oh no, maybe not, I don't want to do that in blue. TA sine 60 is equal to TB sine 45. Okay, and you can leave that there and call that equation number 1 if you want. You can work out any of those values as decimals if you prefer. My preference, though, is going to be writing them out in exact form, because I'm fancy like that. 1 over root 2 TB. It's actually easier in this case to write that as root 2 over 2 lots of TB, because then we can have some nice cancelling going on here. So root 3 TA is equal to root 2 TB, and there's my first equation. Okay, I'm probably going to use that to sub into the other equation in a minute. Newton's second law vertically now, and the reason I said this one's harder is just because there's one more term. So I'm now going to say that up forces, so TA cos 60 and TB cos 45 are equal to all of the down forces, which is 25g. Now cos 60 is a half, so TA over 2, TB, let's work that out. Cos 45 is root 2 over 2 equals 25g. So I can say that TA plus root 2 lots of TB equals 50g, and there's my second equation. And I know that from before, root 2 lots of TB is equal to root 3 lots of TA, and so I'm just going to sub that straight into there. So I can say therefore that TA plus root 3 lots of TA is equal to 50g. And then I'm going to go on to the next slide. Hopefully there's more space for working. There we go. That means if I can factorise TA out of the left-hand side, leaving me 1 plus root 3, and that's still equal to 50g. So TA, therefore, is 50g over 1 plus root 3. And haven't they asked us to show that that's approximately something? Yes, approximately 179. So I'm going to type that in on my calculator. Hopefully it does come out as what I wanted to. Plus root 3. Oh, look, approximately 179 newtons. And then TB, therefore, if you think back to the previous slide, we said that root 3 TA was equal to root 2 TB. So that means that this is equal to root 3 TA over root 2. And when we sub in the fully correct answer for TA, not the approximation, we get, why is my pen not working? We get approximately 219.7 newtons. And there is my answer. Part B, state a modelling assumption you've made in your solution. So you're going to need to go back and read the question again to see which assumptions we made. So the one that we're not allowed to use is we're not allowed to use the fact that the traffic light is modelled as a particle, because that's given to us in the question. So what we did assume is we modelled the cables as being light. Okay, and that had the effect that the tension was equal throughout each of the individual strings. Okay, cool, moving on. Okay, question 6. We've got a little bit of moments going on here. AB is of length 3.8 and it's uniform. So I'm going to do all my annotations on this diagram here. I can say that the weight is going to be here. Okay, and what other forces have we got? We've got the reaction here at C. We've got the reaction here at D. An object of weight W is placed at A. So I have W. And I'm going to change to a different coloured pen. What do I know? C to D is 1.8. D to B is 0.8. Which means that if the weight of the rod is in the middle, that's 1.9 away from each end. So that there is 1.1, which means I know that that bit there, C to D, is 1.8, and I have 1.1 of it already, so that's 0.7, which means that distance there needs to be 1.2. Okay, now with all of those bits of information, I've got everything I need to be able to work this out. Although I do have 3 unknowns, so I'll probably need to either be told what W is, told what C is, told what the reaction at D is, or told that it's about to rotate about C or something like that. So if we go on to part A now, given that, and there we go, they give us W is 69. So I'm going to take moments about C first of all. So moments about point C. So I'm going to have that the reaction at D and the weight of W are consistent with each other. They're going to be rotating in the same direction, and then the weight of the rod is going to be going in the opposite direction, so the clockwise direction. So let's do that one first of all. So I know that 0.7 times 180 is going to be equal to 1.2 W, and I will sub W in a minute, plus 1.8 lots of RD. Okay, so the right hand side then, 1.2 times 69 is 82.8 plus 1.8D, RD. Now, I'm sure if you were clever, you'd find a common factor to divide through by to make everything nicer, but I'm not going to bother doing that here. The numbers are easy enough. So I'm going to have 0.7 times 180 minus that one. So I get 43.2, which means the reaction at D is going to be 24. Now, the fact that it's a whole number doesn't mean it's right, but it fills me with a lot of hope. Okay, and then what I'm going to do is, rather than taking moments again, because I don't like doing moments if I can possibly avoid it, I'm going to do Newton's second law. I'm going to say that the reaction forces, or the sum of the reaction forces, is equal to the sum of the weights. Okay, so that's 249, and so I can say that RC is 249 minus 24, which I believe is 225. 225 newtons, and there's a lovely 6 marks for us. Let's write down newtons nicely. Okay, moving on. So determine the greatest value of W for which the rod remains in equilibrium. So if I make W heavier and heavier and heavier and heavier, what will happen is eventually we'll get to the point where we rotate about C, and that will mean that the reaction at D is 0. So I can say that at W max, RD will be equal to 0. Okay, so rotate about C. That's what will happen if I make W bigger and bigger and bigger and get it to as heavy as possible. So then if I take moments about point C, I'll have that the moment of W must be equal to the moment of the weight. So that means that 1.2 lots of W will have to be equal to 0.7 lots of 180. So W equals 0.7 times 180 over 1.2. And I think that's 150 times 0.7. So is that 105? Yeah, 105 newtons. Okay, so you obviously work that out on your calculator if you want. And there we go, another nice, easy, straightforward 3 marks. Moving on. Okay, question 7. Now, yeah, this to me, I don't know what it is, but it just immediately looks like a differential equation. And then when I look at it in a bit more detail, I see that I'm given an expression for F here, and then I need to find an expression for V. And I know that the usual way of doing that is by turning F into A, force into acceleration, and then integrating. So that's what we're going to do. We've got F equals 30 over t plus 2 all squared, and then to get A we're going to divide by 1.2. So my expression for A is going to be 30 divided by 1.2, which I think is 25. Yeah, so 25 over t plus 2 all squared, and then I'm going to think of A as dv by dt. I'm going to separate the variables and integrate. Okay, so I'm going to have that dv is equal to 25 t plus 2 to the power minus 2 dt, and I'm going to integrate both sides. Now, because I want an expression for v, I'm going to put the constant of integration on the other side. When I integrate some constant multiplied by t plus 2 to the power minus 2, there's no funky integration going on here. I'm just going to add 1 to the power, divide by the new power, and divide by the derivative of the inside. Okay, so I'm going to get minus 25 t plus 2 to the power minus of 1, and then I'm going to divide by the derivative of the inside, which is 1, and then I've got my constant of integration. Looking back then at the question, I want some initial or boundary conditions, and I'm told that when t is a half, the speed is 20. So at t equals 0.5, v equals 20. So I'm going to have 20 equal to, well, then I'm going to have minus 25 over, so 0.5 plus 2, which is 2.5 plus c, so that bit there is 10, so that's going to give me c equals 30, therefore v equals 30 minus 25 over t plus 2. Write down the limiting value of v as t increases, so when t tends towards infinity, well, this term here is going to be a number over something getting bigger and bigger and bigger and bigger and bigger, so that term is going to tend towards 0. So what that tells me is that v tends towards 30, okay, from below, if anybody's interested. So it gets steadily faster and faster and faster, okay, up to a speed of 30. There we go. Moving on. Time taken to reach a speed of 29, so we're going to have a look and use that expression that we just had and equate it to 29. Okay, so when I rejig that, I'm going to get 25 over t plus 2 equals 1, so t plus 2 equals 25. T equals 23 seconds. Okay, so it takes 23 seconds for this thing to speed up to 29 meters per second, and then it takes the rest of infinity for it to get anywhere close to 30. And we'll move on. Question 8, we got something going up a rough inclined plane, which means the first thing we're going to do is we're going to start off with a diagram. Okay, so there's my inclined plane, there's my horizontal, there's my angle. Ooh, 30, that's very steep, but also a nice angle. There's my thing, my object, whatever it might be, doesn't matter at all. 5g. The deceleration of the object up the plane is that, so it's actually decelerating, so it's accelerating in that direction. Yeah, fine. So we got the weight. It's still moving up the plane though, so I'm going to have my friction in this direction and my normal reaction. So that diagram's not the best one in the world. So as before with your decomposing, you may want to consider these two directions, so parallel to the slope and perpendicular to the slope. Hopefully you all remember from your lessons that this angle here is the same as this angle here, so that is also 30. In any question with friction, my piece of advice would be find an expression for friction first if you can. And to find friction, you're going to need to find r. So we're going to resolve perpendicular to the plane. So we've got r acting out of the plane and then only the component of the weight into the plane. So that is then going to be 5g, and then the component into the plane is going to be cos. Okay, which means that the friction available is less than or equal to 5 mu g cos 30. If you were interested, that is root 3 over 2, so 5 mu g root 3 over 2, if you did want to write it exactly. Okay. Now we've got that, I think we can resolve parallel to the slope. Okay, my advice would be take the direction of acceleration as positive, and then thinking about the forces that we've got, well, we've got everything acting down the slope, haven't we? So we've got friction plus 5g sine 30, they're both acting down the slope. Nothing is trying to make this particle move up the slope, so that's equal to 5 multiplied by the acceleration, which is 6.3. Okay, so now I'm going to use my exact version for the friction. 5 mu g root 3 over 2 plus 5g times, well, sine 30 is a half, and that's equal to 5 multiplied by 6.3. You may be wondering why I haven't done all the multiply by 5s, and that's because it is a factor everywhere. I'm also going to multiply through by that, the 2 that's in the denominator of the left hand side. So I'm going to have root 3g times mu plus g equals 12.6. Root 3g mu equals 12.6 minus g. So mu is going to be 12.6 minus g over root 3g. And as usual with mechanics questions, that's going to come out nicely. 2 root 3 over 12. And if you really want to find an approximation for that, it's about 0.1650. Okay, but obviously the exact one's better. Oh, it's a show that. I didn't realise the question was a show that, so yeah, you can't do this bit. We don't want that. We want the exact version. Okay, moving on. I've just spotted a typo on here. I said 21, I think, or I hope I said 21, but I wrote 12. There we go, that's better. Apologies. Moving on again. Okay, determine whether the object will remain stationary after it comes to rest. So I'm going to draw a bigger diagram this time. So there we are here. So if it is at rest, okay, so let's just imagine well, all it's got is this weight acting this way, and then if I do perpendicular to the plane in red and parallel to the plane there, we can see that the only thing that is trying to get this to move down the plane here is this 5g, and it's going to be sine 30, isn't it? Okay, now if this was a smooth plane, this thing would absolutely definitely move because we've got nothing stopping it moving down the slope. It's just going to have its weight, a component of its weight putting it down. But it's not a smooth plane, it's a rough plane, and so we know this blue one is trying to make it move down. That's the only one trying to make it move down, and so there must be then some kind of friction acting up the plane. So we've got a bunch of different situations here, or a few different situations here. If the amount of friction available is greater than or equal to this 5g sine 30, this object will remain at rest, because remember, friction never tries to induce motion, or it never induces motion. So if there were 100 newtons of friction available to be used, but the component of the weight down the slope is only 50, well then no motion would happen. The only situation in which motion would occur is if the blue force that I've got written there is greater than the friction available. So let's remind ourselves, what is the magnitude of the friction? So F max is equal to, and we worked it out, I think, in the last question, it was mu times r, wasn't it? So it was 2 root 3 over 21. So 2 root 3 over 21 multiplied by 5g cos 30, and if you type all of that into your calculator, you'll find that you've got 7. Okay, so that means we have a pool of 7 newtons worth of friction to play with here. So then let's just evaluate 5g sine 30. and see what that is. So 5 times 9.8 times sine of 30, that is 24.5. Okay, so what we can say here is that the amount of weight available is greater than the amount of friction that we've got available to try and stop motion. So what we can say is no, the object will not remain stationary since 24.5 is greater than the friction available. Okay, so yeah, I need to look at the size of both of these forces. Okay, moving on. Okay, so I guess looking at this question, what we know is definitely to do with vectors, but my guess is there's probably some kind of projectiles question coming later, given that this is the final question and we haven't had projectiles yet. So find an expression for velocity vector. Remember, we know that the velocity vector is the rate of change of the displacement vector or position vector, and I'm going to choose to write these as column vectors. So we're going to differentiate both with respect to t, giving us 8t, and then t cubed 1.5, so plus 9 lots of t to the half. Okay, that's the general one, hence find the velocity vector when t equals 4. So v when t equals 4, well, I'm going to get 32 here. I'm going to get 4 cubed, which is 64, plus 18, which I believe is 82. Yeah, 82. And there's my first 3 marks on this question. Lovely. Moving on. And here's the projectiles. At t equals 4, R runs out of fuel, so it's a rocket then that's not got any more propulsion, so it's going to fall freely under gravity and behave like a projectile. Show that R takes approximately 18 seconds to reach the ground after the fuel runs out. Okay, so this feels like we're going to do some SUVAT. What we know is that initially, we know what the speed is, don't we? We know that it's this. We just found it out. We can work out what the position vector is as well by subbing t equals 4 back into our original expression, and you get 64 and 112. Okay. And we want to know, so it's got to reach the ground. That's the bit that we're interested in. Okay, and we're not going to use the 18. We're going to get to the 18 for ourselves. So I'm thinking of using a SUVAT equation. I'm going to do it just in one dimension. So I'm going to say in the vertical direction, I know u is equal to 82, a is equal to minus 9.8, time is what I want to find, and then the last thing is the displacement. Relative to where it is, I want it to be at the floor, which is 112 meters below that. So I'm going to use s equals ut plus at squared over 2. Therefore, minus 112 equals 82t minus 4.9 t squared. Now, there is a chance that when I write this as a quadratic in terms of t, I'll be able to factorize it. Not a very big chance, I don't think, because the numbers look a bit icky. But what I'm then going to do is I'm going to use my calculator, and on mechanics and stats papers, you are allowed to just use your calculator to find solutions. You do not need to show me the fact that you've used the quadratic formula. Okay, that's something where you absolutely need to do it on a pure paper, but on applied papers you don't need to. So I'm going to go into the polynomial solver, degree 2, so I've got 4.9, minus 82 and minus 112, and I get one solution of 18.004, so that's pretty close, and then the other solution is negative, therefore approx 18, oops, the daisies, 18 seconds. I'm going to write the other one in red. T equals minus 1.2695, and we're going to obviously ignore that one. Okay, hence determine whether R lands within the safe zone, given that the safe zone is 600 meters. So I forgot to say this is dotty 1, and then let's do dotty 2. So what we really need to know is how far it travelled in those 18 seconds. Okay, so horizontally now, we know that it's going to travel 32 meters per second. Okay, it's not going to slow down, remember, projectiles, the horizontal acceleration is 0. It's going to do that 32 meters per second for 18 seconds, but then also during the booster phase, I think it was called, it travels 64 meters horizontally. Okay, so this bit here is how far it travels when it was just acting as a projectile, when it was just falling, and this bit here was during the booster phase. So when I then work that out, when I work that out, 32 times 18, 32 times 18 plus the 64, I get that that is 640 meters. Now, since 640 is greater than 600, no, it does not land in the safe zone. Does not land in the safe zone. Okay. Remember to write that written explanation at the end. Just get into the 640, and realistically writing 640 greater than 600, that's not going to be enough to get you that second mark. So I need to know that you know what that 640 is and what it represents relative to the 600. So we'd want to see that explanation at the end. Okay, and there we go, all done. Okay, thanks, bye-bye.